Hello, and welcome to our video covering topics in section 6.1 and 6.2 of your textbook. In this video, we will discuss the definition of the determinant and some properties of the determinant. And then if you have the stamina, you can stick around for some bonus content where we talk about some possible alternate definitions of the determinant. Okay. So let's take a trip down memory lane and remind ourselves, where did these come from? Where did we first see determinants? So you remember that time I asked you, maybe on a pre-assignment or homework or something, to calculate the inverse of A, B, C, D by hand? Well, you did, and you calculated a reduced row echelon form of this matrix, and you got this. And then we said, oh, notice that the matrix is invertible exactly when AD minus BC is not equal to 0. And then we called AD minus BC the determinant, and we thought of it as a calculation for testing invertibility. All right, well, if I went through a similar exercise and asked you to calculate the inverse of this generic 3 by 3 matrix by hand, you would get justifiably angry. But also, if you did it, you would get that the reduced row echelon form of this matrix is that mess. And the reason it looks blurry is because, I just copied and pasted that from Wolfram Alpha. I am, life's too short to have actually calculated that by hand, and life's too short to even have typed it out by hand. Anyhow, but notice that the matrix is invertible when this term here, which shows up in the denominators, when that's non-zero. And you might be thinking, wait, why did I choose this one and not the negative? We'll give a reason for choosing this one in a moment. But yes, this, again, thinking of this as all right, well, what do we need to make the determinant non-zero? We'll call, or to make the what number is non-zero if and only if the matrix is invertible? Then it's that mess right there. Oh, geez. Okay, let's move on. So basically, the determinant of a square matrix, it's going to be some scalar function, meaning it's taking a matrix and it's some function of the entries of the matrix, but it spits out a number. And it has this property that the matrix is invertible if and only if the number it spits out is non-zero. And then, okay, if you really wanted to, you can calculate the determinant by calculating the general inverse and finding a common denominator, check the common denominator. And oh boy, that's terrible and only 3 by 3. And I'm also admitting that for the moment, this is leaving the determinant, the sign of the determinant, ambiguous. But actually, it turns out there are several equivalent ways of formally defining the determinant. And so here, let's walk our way towards one formal definition. So we already know the determinant of 2 by 2 matrix, and from Wolfram Alpha, we know what the determinant of a 3 by 3 matrix, general matrix is. And we notice that there are some properties that these two determinants have in common. So one, in both cases, the determinant of the identity matrix is 1. This is something that you've already confirmed in your pre-assignment for the 2 by 2 case, but we can check quickly that this is also true in the 3 by 3 case. So A1122, A33, if this is identity, that's going to multiply out to 1. And then all these other terms have an off diagonal on them, so all these other terms are going to be 0. And in fact, this is the kind of property that determines the sign for us, because we want, this makes sense, right? We want the determinant of the identity matrix to be 1, given how we calculated them. It's also the case, not that you would just notice this, but it is the case that if you swap rows, then the sign of the determinant changes. And again, you confirmed this in your pre-assignment for the 2 by 2 case, and you can check this for the 3 by 3 case also. A little bit more of a hassle, but you can do it. But boy, is it a hassle in higher dimensions. but it happens to be also true in higher dimensions. And then finally, and I definitely don't think you would have noticed this on your own. I certainly wouldn't have. But it turns out that the determinant is linear in each row. So let's take a moment to see what I mean by that. And actually, let's see, here's what I don't mean. To say that the determinant is linear in each row does not mean that you can just pull out a scalar or distribute over addition. In fact, in general, these things are super not true. So, okay. What do I mean then? Well, when I say it's linear, the determinant is linear in each row, that means, all right, let's look at a 3x3 case. Suppose we're fixing the first two rows, B1 and B2. And we're saying, okay, leaving these rows alone, suppose the third row is the sum of two row vectors, x and y. Then you can split up the determinant over a row. So the determinant of this matrix is the determinant of the matrix where the last row is x plus the determinant where the last row is y. And then in 3x3 case, we're fixing the first two rows. If you scale one row by k, then you can pull k out of that row. And then you have the determinant of this matrix is k, or the determinant of this matrix is k times the determinant of this matrix. This is something that you confirmed in the 2x2 case already, but it also holds in the 3x3 case. Okay. So, all right, let's get on paper our formal definition. And this is actually not from your book. This is from the book Introduction to Linear Algebra by Gilbert Strang. This is a book they use at MIT. And I'll give you, at the end of this slide, I'll tell you why I like it. So it turns out that the determinant is the unique function from Rn by n to R with the following three properties. The identity property says that the determinant of the n by n identity matrix is 1. The alternating property says that the determinant changes sign when two rows are exchanged. And the linearity in each row property, and there's probably a better term for that, but I don't have one. And this is the property that the determinant is a linear function of each row separately. Okay, so yeah, it turns out that a function with these three properties is that captures the notion of the determinant, and that's all you need, which is surprising. I would say, to say the least, it's surprising that that's all you need, and that really is capturing the determinant. I'm a little worried that I missed something here. Yeah, okay. This is just the general way of writing out the linearity in each row, where it's just, all right, you've got n by n matrix, and then you're just choosing some random row to be linear across. Okay. All right, so why choose this definition? Well, one, it's easy to state, way easier to state, in my opinion, than your alternate definitions. And two, tons of easy properties of the determinant follow from this definition and are kind of a pain using the other definitions. So this is, in some sense, this is the slickest definition, which is why I'm going for it, because I'm going to insist on proving some stuff. But Con, I'm the first to admit it's not at all obvious that this definition captures what we're after, and it also doesn't really provide an obvious method of calculation. But yeah, this is the one we're going to go with. So we're departing somewhat significantly from your book for a little bit. All right, let's talk about some properties of the determinant. We have some quick results given the definition that we chose. So first, if two rows of a matrix are equal, then the determinant is 0. This is discussed in an example in your book. So why is this true? Well, if two rows are equal, then swapping those two rows leaves A unchanged. But by the alternating property, this means that swapping two rows means you have to change the sign, and so the determinant of A will then be equal to minus the determinant of A. and the only number equal to its negation is 0. And so if 2 rows are equal, the determinant is 0. That should be a relief, since if 2 rows are equal, it's not invertible, and so we wanted it to be 0. And there you go. Another quick result that we want to be true is that if a row is all zeros, then again the determinant is 0. This is again also discussed in your book. And let's see how we can show this given, I think we use the linearity property. So, okay, suppose you have matrix A and one of the rows is 0. Then notice that we can say, all right, the determinant of A, so the determinant of A is this, because this is matrix A, and then I'm adding 0 by taking the determinant of this matrix that has V1 twice. So V1 shows up in the first row, but then I'm saying, all right, let's duplicate the first row in the row where A has a 0. So determinant of A plus 0 is the determinant of A. And then let's use linearity and combine these. So now that's equal to the determinant of this matrix. But notice 0 plus V1 is just V1. And so this really is a matrix with 2 rows that are equal, which by their first quick result says that determinant has to be 0. So good, because again, if all rows are 0, then it's not invertible. The determinant better, or if a row has all zeros, then it's not invertible. The determinant better be 0. Okay, let's see how we can calculate the determinant of a diagonal matrix using just what we know. All right, so diagonal matrix, it's got entries, possible non-zero entries on the diagonal, 0 everywhere else. Well, let's use that linearity property. In the first row, we're going to factor out an A11. Right. So factoring out we can factor out from the row because it's linear in the first row. But similarly, next we can factor out A22 from the second row because it's linear in the second row also. And so forth, we just factor out from each row, each coefficient. And so this is equal to A11, A22, AN, all the way up to ANN times the determinant of this matrix. But this is the identity matrix, and so the determinant just is the product of the entries. And notice that if one of these entries was 0 to begin with, then we would have had a row of all zeros, and we know that the determinant is 0. So if you're worried that I was assuming that these were all non-zero, no, I knew what I was doing. Yeah. So the determinant of a diagonal matrix is the product of its entries. And this is the theorem in your book. This leads me to just let you know about possibly the greatest linear algebra professor quote of all time. And it goes something like this. If you were to ask me if I'd rather compute the determinant of a 100 by 100 matrix or accept the sweet release of death, I'd probably choose death. Unless it was a diagonal matrix, of course. So good. Anyway, if you've never encountered math professor quotes, it's quite enjoyable. All right, enough goofing around. Let's see how row operations act with determinants. This is going to be really important. So, all right. If matrix B is obtained from matrix A by dividing a row of A by a scalar k, then the determinant of B is 1 over k times the determinant of A. So first, this is just saying one of our elementary row operations is to multiply or divide by a scalar, multiply or divide a row by a scalar. And this is saying, okay, well, how does that affect the determinant? Well, you can, by the linearity property, all right, whatever row you scaled by 1 over k, you can factor that out of the determinant. So the determinant of the resulting matrix is just the determinant of A, but with the scalar 1 over k pulled out. Okay, another elementary row operation is row swap. We've already seen, okay, if you swap two rows, then the determinant changes sign. This is just a statement of the alternating property. And then finally, if the matrix is obtained by adding a multiple of one row to another, then the determinant doesn't change. So let's see why that's true. So suppose we've got some matrix A, right, V1 up to Vi, Vj, Vn. Then the determinant of adding a multiple of one row to another, so here we're adding a multiple of Vj to Vi, so we're saying Vi plus kvj. What is that? Well, using the linearity in this row, that's equal to the determinant of V1 to Vn plus k times the determinant of this matrix. But notice that this matrix now has Vj in two rows. And so any matrix that has two rows that are the same is going to have determinant 0. And so this whole thing is going to be 0. And so we're left just with this term, which was A. So adding the multiple of a row doesn't change the determinant. And so that's due purely to the linearity in each row. So you might see now a little bit of the motivation for choosing the definition that we did, because from linearity and alternating property tells us how row operations affect determinants, and then the identity property is just telling us what sign we needed to use. So, okay, now we know how row operations and determinants play together. Let's see some consequences of this. So, all right, this is the holy grail. We need this to be true. If our definition is any good at all, we should be able to prove that a square matrix is invertible if and only if the determinant's non-zero. So, okay, suppose that during Gauss-Jordan elimination, we swap rows s times, divide various rows by the scalars k1 to kr, and add multiples of one row to another various times to get to the reduced row echelon form. So these are the only things we can do. We can do row swaps, we can divide by scalars, and we can add multiples of one row to another. Well, given what we just saw, this means that the determinant of the reduced row echelon form of A is going to be -1 times the number of swaps, since every swap is going to change the sign. And then, okay, we pull out all of the scalars every time we scaled a row by, or, divided a row by one of these. We multiplied by the scalar 1 over k sub I, pulled them all out. And then remember, adding multiples of row doesn't do anything at all to the reduced row echelon form. So, it doesn't do anything at all to the determinant. So we get this, that the determinant of the reduced row echelon form, -1 to the s, times 1 over all this scalars, or the scalars you divided by, times the determinant of A. And just rearrange, solve for the determinant of A. Looks like this. Now notice, if A is invertible, then reduced row echelon form of A is 1, and the determinant of A, in this case, would be not 0, because all of the scalars that we're dividing by, we're not dividing by 0 at any time in Gauss-Jordan or in life. So yes, these are all non-zero. If A is invertible, this is going to be 1. The determinant of A is non-zero. And if A is not invertible, then the reduced row echelon form of A is going to have a row of zeros. And that means the determinant of the reduced row echelon form of A is going to be 0, which means this whole term is going to be 0, which means the determinant of A is going to be 0. Whew, good. Glad we have that under our belts. And now let's calculate the determinant of a triangular matrix, either upper or lower. And we're going to show that actually the determinant is the product of the diagonal entries of the matrix, just like for a diagonal matrix. So that's nice. Let's see why that's true. So let's say you have an upper triangular matrix. Argument's going to be very similar if you have a lower triangular matrix. So you've got an upper triangular matrix. And now If each diagonal entry is non-zero, then you can use Gauss-Jordan elimination to add and subtract multiples of rows below to cancel all the off diagonal entries. So like, oh yeah, you want to get rid of A12, we'll just subtract the multiple of A22 from here and to the one that makes that 0. So, and similarly, like A1n, just subtract a multiple of this last row to get to cancel that and all the other terms. But remember, using adding and subtracting multiples of rows does not change the determinant at all. And so without changing the determinant, you can use Gauss-Jordan elimination to just, and you're not changing the diagonals either because you're only using like the rows below to get rid of these. Then, all right, you have a diagonal matrix, and we've already seen the diagonal matrix. The determinant is the product of its diagonal entries. And there you go. And then, well, what if one of the diagonal entries was actually 0? Well, then the matrix isn't invertible because you can see kind of right away that if one of these is 0, then you're not going to have full rank. And so the matrix isn't going to be invertible. And as we've already seen, the determinant will then be 0. In which case, it's still the product of the entries because one of these will be 0, and so the whole product will be 0. So there we go. So if you're asked to find the determinant, just pray that it's a diagonal or a triangular matrix. But okay, if prayer doesn't work, let's give you at least one method for actually calculating determinants in this video. So using Gauss-Jordan elimination, if you have an invertible n by n matrix, suppose you swap rows s times as you compute the reduced row echelon form, and you find various rows by, and you divide various rows by the scalars. You don't have to worry about row swaps, doesn't change anything. Then this is basically the equation we already saw. The determinant is just -1 times the row swaps times the scalars you divide it by. But notice, you don't actually have to reduce all the way to the reduced row echelon form. And so you can use elementary row operations to transform A into some matrix B, where the determinant's easy to compute, like a triangular matrix, for example. And so, I actually think this is what computers do sometimes. Computers certainly don't do what we suggested in the first slides of finding the inverse of a general matrix and like getting the formula that way. No way. So yeah, I think computers will do something like this. They'll row reduce and keep track of swaps and scalars until it gets a triangular matrix, and then just take the product of the diagonals for that. So it'd be this times determinant of the triangular matrix, which this would be the product of the diagonals. Okay, and your book goes through a nice example, and so in your pre-assignment, I have you read through that example, and I trust you can do it. All right, so that was it for the required content. Yeah, so let's, if you've got the stamina, let's talk about some alternate definitions. So here's the definition you probably wanted, given how we set up determinants. You might notice that the determinant of just a 1-by-1 matrix is the entry. The determinant of a 2-by-2 matrix we calculated. Determinant of a 3-by-3 matrix we calculated. You can't see the scare quotes when I said that, but I did put them. I did, use my fingers to do them. If we tried to calculate a 4-by-4 matrix determinant, we would get something like this. And you're like, wait, why did all of these become uppercase A's? And it's just because I copied and pasted this from the internet. Literally did not check if this was true, assuming that it is. So yeah, what you probably wanted is we say, all right, so we've calculated these determinants and figure out the pattern. And so this is actually the method your book kind of goes through. So here's your book's definition. And what they do is really rely heavily on the 3-by-3 case and then kind of just say this generalizes. So in the 3x3 case, all right, this is RA, this is our determinant. And your book says, all right, well, let's look at these entries and let's see, like, where do these entries fall in the matrix? And so these first ones are the diagonal entries. And how about in this term? What are the entries? Okay, they're these. In this term, circle the entries. 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 And what your book says is, oh, notice that for each of these terms, it's a product of three factors, and those factors are each involve exactly one entry from each row and column. So here, one entry from this row and column and row, one entry from this row and column, and one entry from this row and column. And same for all of these. And then your book calls such a choice of factors, where you choose one from each row and each column, they call that a pattern. And so these terms here are terms from all possible patterns. So it's not just that each of these terms like represents a pattern, but also every possible pattern is represented up here. And so actually this term your book would call the product of the pattern. Like this is a pattern and this would be the product of the pattern. But okay, I think hopefully you get the idea. So okay, the terms are all identified with patterns. And then how are the signs determined? Well, your book says, say that two numbers in a pattern are inverted if one of them is to the right and above the other. So in this, there's no inversions, like no number is to the right and above another. But in this one, we have two inversions because A12 and A23 are both to the right and above A31. Similarly, this has two inversions because A13 is above and to the right of both A21 and A32. This, you might think, has two inversions, but actually it's three because both of these are above A31 and this is above A22. All right, this is one inversion and that has one inversion. And then they say, notice that the sign is positive if the number of inversions is even and negative if the number of inversions is odd. And they say, okay, generalizing these observations, and you could confirm that these work in the 1x1, 2x2. They do it for 3x3. You could confirm it for the 4x4 if you hated your free time. Then they say, all right, the determinant is then going to be what you get when you take a pattern, have number one, or have negative one raised to the number of inversions. That will make it, even if the number of inversions is, or it'll make it 1 if the number is even and negative 1 if it's odd. Okay. Negative 1 times the number of inversions in a pattern times the product of the entries in the pattern, and then you sum over all possible patterns, which is like a lot. It's like n factorial, which is, that grows really quickly. But anyway, so this is your book's definition of the determinant. And I'm just going to say this is not the most rigorous. Like a more rigorous version of this definition is in the language of permutations. And so I'm not going to spend a lot of time on this slide. I'm just giving this to you. It's the same thing, but basically in the language of permutations. And where did this come from? Well, this actually came from my own linear algebra professor. Thank you, Professor Robert Winters. So this is something that, I saw when I was taking linear algebra. But, so there it is. It's just the sign and, okay, the subscripts. This is just, all in the set of all about permutations. So if you know about permutations, then you can read this and try to puzzle through and make sure that it agrees with what we've already seen. And otherwise just say okay, I hope this never comes up again in my life. So here's the pro of a definition like this or your books. It does seem like the most natural definition given how we define the determinant in lower dimensions, or at least how we found the determinant by finding denominators like this and looking at the pattern. This seems like the most natural one. It's really not the best suited for either calculations or proofs, which is why I ended up not going with it. So yeah, I went with the version that's most suited for proofs, and other books might go for this one or the one that's best suited for calculations. And indeed, previous editions of your textbook went with a different definition. They went with the recursive definition of the determinant. And so here, again, let's rely on the 3x3 case to kind of generalize. So that's the determinant in the 3x3 case. Notice that you can do some rearranging and some factoring out, and you factor out these terms A11, A22, A31, and you get three things that look like 2x2 determinants. And in fact, your book notes, because your book talks about this, but it's a theorem, not a definition, says, okay, well, the determinant of A is you get A11, so this first term, the first entry, and this here is A11 times the determinant of the matrix you would get if you crossed out the row and column that A11 is in. And then if you factor out an minus A21 here, then the negative of this is the determinant of the matrix you would get if you crossed out the column and row of that A21 was in. So it's this determinant here. And then this last term is A31 times the determinant of the matrix you would get if you crossed out the column and row here. So say, okay, well, what's the pattern? Well, first they say, all right, if your matrix A is just a general n by n matrix, then they say A sub ij is the term they use to describe the n minus 1 by n minus 1 matrix that you get by crossing out row I and column j. And then they say, okay, you can rewrite the determinant of A as saying, okay, well, it's A, so this is what we had before, and then they would write that more compactly as A11 times the determinant of capital A11 minus A21 times the determinant of capital A21 plus A31 times the determinant of capital A31. And then in general, I guess one thing to say is the signs alternate. So you've got plus, minus, plus. And we'll see in what they have as this theorem, which again, some books use as the definition and previous versions of your book uses the definition. You've got what they call the Laplace expansion or cofactor expansion. And this says that, okay, expanding down the jth column. So not only, so in the, what we just saw, we expanded down the first column. And the claim is actually you can expand down any column or any row, so long as it follows this pattern. You have -1 times the, so I guess if you're going down a column, then you're looking at if you're looking in the jth column, then you're summing over the I and I different rows in that column. And if you just sum over the i's, it's -1 to I plus j. So if your entry is in a column and row where I plus j is even, then A11, I plus j is 2, so that's even, so it's going to be positive. But if I plus j is odd, it's going to be negative. And then you have the term, and then it's times the determinant that you get by crossing out that row and column, and then you sum over every entry in that row. And so this leads to a method of calculating, because you say all right, we already know what a 2x2 matrix determinant is, and we have a formula for the 3x3 matrix determinant. So what's a formula for the 4 by 4 determinant? Well, okay, you can define it in terms of 3 by 3 determinants. It's a pain, but it's doable. And then once you've got that, all right, if you have a 7 by 7 matrix and you want to know its determinant, well, all right, expand down a column and you get it into a bunch of 6 by 6 determinants. Now for each of those, expand down a column, so you get a bunch of 5 by 5 determinants. Expand down a column, you get a bunch of 4 by 4 determinants, and then maybe you get it down to 3 by 3 determinants, and you've definitely made a calculation error at this point. But in theory, you've got your method. All right, so this immediately leads to a tangible method, especially, really in like the 4 by 4 cases where you're going to use this. But yeah, this isn't actually the slickest or the most intuitive. So, all right, they all have pros and cons. And that, folks, is all we've got for determinants in this video. See you next time.